Okay, so here we go. So 2,500 students take a college entrance exam. The scores of the exam in approximately normal distribution with mean 56, standard deviation 9. Use the blah, blah, blah rule to examine the following. The average score in the exam is approximately. Okay, yeah, so first off, let's go through these questions. When they say average, that's just the middle. That's what the mu is, right? The mu is the middle. So I just grabbed the mean is the average. Next, what percentage of adults scored 56 or less? Well, if we're talking about a bell curve here, right? How do I know it's a bell curve? Normally distributed. That's the key word you'll look for in the test when it's all mixed up with the other chapter. Look for normally distributed. That's when you know it's the normal curve, the bell curve. So the middle. What's the middle? Well, they're telling me the middle's 56 when they tell me the mean, is 56, huh? So the middle's 56, and so, I got the 3 lines to the left and the 3 lines to the right and all that. Well, what percent is 56 or less? Well, 56 is the middle. What percentage is left of that? It's got to be 50%. It's the middle, so half the curve is below it. Right? That's what it means to be the middle. 50% is below you and 50% is above you. All right, next question. Approximately what percentage of students scored between 47 and 65? Well, how do I figure that out? Well, I got to do, remember, these numbers are not percentages, right? So that means they're down below, huh? Y'all with me? Percentages up top, non-percentages down below. So 47 and 65 must be numbers down here. They're not percentages. Well, how do I get them? Well, they told me, no, there it is. Sigma's 9. There's the jump from line to line on the bottom, huh? The jump from line to line on the bottom is 9. So that means the middle's 56, add 9, 65. Add 9, what's that, 74, add 9, 83. And the other way, subtract 9, 47, subtract 9, 38, subtract 9, 29. Is that good like I did last time? So we put the middle, 56, and then the jump amount from line to line on the bottom is 9. Now, what's their question? Between 47 and 65. So how many between 47 and 65? Well, that would be all these, because here's 47, here's 65. See those marks right there? So when they say what percentage score between 47 and 65, it's just those 2 middle chunks around the middle. And you know what the percentages are. They're 34 and 34. You'll have those on your 3x5 cards. So 34 and 34, that's the 68. 34 and 34. See how I'm getting that? Is that good for part C? And then part D, approximately what percent scored 65 or more? 65 is not a percentage, so it must be a number down below. 65 or more. More is which way, right or left? To the right. So they're saying on this part D, they're saying how many are at 65 or more to the right. So they want everything from 65 to the right. What are those other percentages? This one is what? 13.5 and 2.35 and 0.15%. That one was 13. Let me write that one a little bit better. 13.5. So yes, we have to add up this, and this, right? For part D. Oops. So it's 13.5. and 2.35 and 0.15. What is all that? 16%? Yeah, 16. Oh yeah, there's right there. So they add up to 16%. Is that good? Does that make sense on that? Now, in a minute, they're going to ask the same question, but change it ever so slightly. They're going to say how, instead of saying what percentage, like they just did on this one, like what percentage of students scored 65 or more, they'll say how many students. So how would I take the 16% and turn that into how many students? How many total? 2,500, you can read that. 2,500 total in the whole curve. So you just take your percentage, make it a decimal, 0.16 times 2,500, right? So when they ask us actual people, we'll just multiply the percentage decimal form times the total. We'll get 16% of the 2,500 people times, of means times. Yeah, that'll be coming in these next questions. Any other questions on that one? This one, they just wanted the percentages. All right. Okay. So whenever they talk about the quartile stuff, you got to use that. Remember the formula I gave you yesterday? Q1. I don't mean you have it memorized, but I remember I gave it. What was it? It was mu minus. Was it like? I don't remember. 0.3. No, I don't remember. I'm just guessing. Somebody remember? We have it.
0.675.
Yeah, 0.675. That's it. 0.675 sigma. That's Q1. And Q3 is mu plus, because it's to the right, 0.675 sigma. Yeah, so whenever they speak for bell curves anyway, so we're in the bell curve normal distribution section. It says right here, normally distributed. That's the words that you want to jump off the page for you on the test tomorrow. They're giving me the mean, and they're giving me the standard deviation. So yeah, I can find Q1. Q1 is just the mean. 57 minus 0.675 times sigma. Sigma's 13. That'll come out 48.2 rounded to one decimal place. And then for the next part, Q3, I'll do that one down here. Q3 is mu plus 0.675 sigma. So that's 57 plus 0.675 sigma. What's sigma? 13. And then that's where you get the 65.8. Like that. That's the Q3 like that. And so there we go. We have Q1 and we have Q3. Is that good? Questions I can answer on that? Question, Jenna?
Yeah. Okay. When you said the normal distribution, what did you say that was associated with the bell curve, or was it?
Right, and then I didn't draw the bell curve, huh? Yeah, that's a good question. Yeah, I don't mean you have to actually draw bell curve. I just mean this Q1 formula and Q3 formula are from the bell curve. Okay. They're yeah. So whenever they say normally distributed and they mention either the quartiles, use those formulas. Yeah, I didn't actually have to draw the bell curve on this one, did I? All they asked me for was the Q1, Q3. Yeah, good question. Makes sense? Yeah, so that's what I'm really meaning. I didn't actually draw the bell curve. I just used the Q1, Q3 formula when they mentioned the quartiles with normal distribution. Good. Other questions on that one? That good? Okay. So this one, they're going to actually ask number of people. So we're going to get the percentage and then multiply by the total number. All right, here we go. Research project, blood pressures, blah, blah, blah. And so there's the key words. Approximately normal distribution. That means the results are belled. They're humped in the middle, right? Bell curve, big pile in the middle. And the other way, when they say, oh, I didn't mention, you might wonder, like, what is that 68, 95, 99.7 rule? That's the percentages if you add up the middle 2, middle 4, middle 6. That's what you'll get. Let me show you. Let me just draw the curve again. So here we go again. It's going to be all about the curve again. It was kind of so-so. All right, good enough. So we got the middle. 1 jump to the right, 2 jumps to the right, 3 jumps to the right, 1 jump left, 2 jumps left, 3 jumps left. And so the middle, they're telling me the middle is, what, 127. So the middle's 127. I'll just put that right in the middle. Here's the middle. And they're telling me each of the jumps, how much is it from line to line? Not making sense? How much is it going to be from line to line in this?
13.
Yeah, that 13. Right, exactly. Is everybody With Quez on that one, he's right. Everybody good with that? See that? That's correct. 13. So yes, so add the 13 there. It's at 140. And then add the 13. It'd be 153. And then add the 13, 1. What's that? 66. And then subtract 13, 114. Subtract 13, 101. Subtract 13, is it 88? No. Yeah, that's right, huh? 98, yeah, that's right, 88. So there we go for that. And the percentages, those are always the same. So I'll just write those in right now. 34%, 34%. 13.5, 13.5, 2.35, 0.15, 2.35, 0.15. Good there. So it's pretty much almost all these problems, huh? We just draw the bell curve, put the percentages in, those are always the same, and then we find the middle, they give you the middle, and then they tell you how much to add for every line jump and how much to subtract the other way. So now, so we do that before I even think really about their questions. Now here comes their question. Estimate the number of patients whose blood pressure was 114 or higher. The 114 is not a percentage, so I'm looking at the bottom, and there it is. So they're saying, how many are 114 right here on this line, or higher? Which way is higher, right or left? To the right. So they're saying, how many are 114 or higher, or to the right? So how many from the 114 line to the right? So first off, how do I figure the percentage from the 114 line to the right? How much from the middle to the right? 50%, right? Because it's the middle. And then how much here? 34. So from here all the way over must be 84%, because it's 50 plus 34. Does that make sense? We're not done yet. We're almost done with part A. So it's 80. So from the 114 line to the right must be 34 and 50, right? 84%. So then you take that 84%, you want 84% of all the patients. How many are all the patients? Right up here, 3,000. So you want 84% of the 3,000 patients. So 0.84 times 3,000, huh? Is that good? And that must come out to be the 2520 number for part A. That's all part A. Then we'll do part B. But everybody okay with that one? Now part B, how many had between 114 and what is that other number? And 153. So how many had between 114 and 153? So here's 114 again, and 153 is here. So 114 to 153 is all of that, huh? 114 to 153, 114 to 153. That's part B. That section right there, 114 to 153. So then just add up those percentages, huh? Just add those up. So 34%, 34%, and 13.5. So part B would be 34%, 34%, and 13.5. 68, 78, 78. Is it 81.5%? I think there, right, 81.5%. But they don't want percentage, they want actual people, patients. don't they? So same thing as last time. So you take the 0.815, you change it to decimal, move it back 2 places, right? Times the 3,000 patients, and you get the answer 2445. Like that. For part B. Is that good? This making sense? It's all about that curve, isn't it? It's just question after question after question about that bell curve. The percentages are always the same. We just have to put the middle on the bottom and then add the jump amount. Then just give them what they want for the percentages. And multiply by the total number if they want people. Is that okay? Other questions I can answer on that one? All right. Why do they say the whole 68? I'll just give you the reason why. Why do they say this weird thing here about like 68, 95, 99? Do you see if you take the two middle, the 34 and the 34, if you add them up, that's the 68. And then if you go one wider, you go a little wider, and you take the 4 middle from there to there. Can you read that? It's kind of a funny concept. There to there. If you add up 13.5, 34, 34, and the other 13.5, you'll get, 95. You'll get 95. And then if you go even one wider, from there to there, three to the left, 3 to the right, add them all up, you'll get the 99.7. So that's what they mean by when they say, use the 68, 95, 99.7 rule. That means use the bell curve. That's just another way of saying, but those are the regions in the bell curve. 1 jump right and left, 2 jumps right and left, 3 jumps right and left. That's all that is. It's just another way of saying use the bell curve, use the normal curve, use the Gaussian curve, use the 68, 95, 99.7 rule. It just means that's how data normally distributes. 50 plus 34 plus 13.5. Everybody see that? 50 plus 34 plus 13.5. 84, 94, 97.5, and that's the answer. See how we're doing that? Not making good sense? So it's very, very likely that you're going to get a bag of chips coming out 25.5 ounces or less. 97.5% of all bags do that. Very rare that the machine gives you more than 25.5 ounces of chips. All right, so all kinds of things in life, they monitor this. This was a lot, I'm always a wannabe history teacher, and they do a little bit of history. It's interesting. I'll just keep it really, really quick. We get ready for a test. But a guy named Deming was the guy that applied a lot of this variability stuff to manufacturing processes to help make cars better. So he brought in a lot of this statistics to the making of cars. Because, when they make cars, they want to make them well so they last. And when temperatures are hotter, colder, metals expand. That's why things aren't always made. It's one of the reasons things aren't always made perfect on the cars. Like, why isn't every whatever car, why isn't every 1999 Chevy Nova exactly the same? Or that didn't make sure. Anyway, whatever. I'm just picking a thing at random. Well, why aren't they all exactly the same? Well, they're using the same things, but temperatures vary. And so things vary with temperatures and water in the air, and when they heat the metals and do different things. So Deming was one of the first ones that really showed manufacturing plants how to use statistics to carefully measure their products to make everything more exactly the same. And you know who he did it for? He did it right after World War II, so it's 1950s, for a country that had been wiped out by World War II, but was now willing to start manufacturing things. Japan. And you know what they did, right? They became a world leader in exporting cars. Deming became world famous, actually, because of his statistical work. That actually he showed the Japanese, he went over there, and he showed the Japanese how to use these statistics to make their cars better. And we all know the story of history now, right? In 10 to 20 years, the Japanese cars took over the market because they were superior. That's why I own like 4 Toyotas. Because they're just, now they're made in America and everything. But really, it was those improved processing things. And in fact, it was funny, there was a big special done. Like, he came to America. Deming was from America, actually. He was a guy from America. He had his PhD in physics or something from an American university. He was an American guy from the South, born and raised here. But he offered his services to some of the big American car makers in the 50s, you know, Ford and Chevy, and they weren't interested. So he went overseas to the Japanese, transformed them. He's like a folk hero in Japan. They actually made, what did they do? They did something cute. They gave him the #1 award for business. Like, he was like a folk hero, literally, without exaggeration. You could type it in. You type it into Google, you read all of it. He died probably 10 years ago, 20 years ago. But Deming was a folk hero in Japan. He was like, because, you know, he transformed, they would pay him millions of dollars to come to his factories and tell the people how to manage things better, and he made them millions of dollars. And then finally, in the 1970s, I think, ABC or NBC, one of those stations, did a special on him, all about him, half-an-hour show about Deming. And the title of the show was, "If Japan can do it, why can't we?" Right? And they just showed how the Japanese industry was following Deming's advice, and it was working great. And right after that, Deming started getting calls from, after that special was on ABC or NBC, whatever, he started getting calls from Ford and all the American manufacturers, and then they had him come in and he helped transform our processes as well. So anyway, he's kind of a folk hero in the whole thing. It was all based on statistics, and he showed them how to use that in processing to make things better, as we know. All right, let's look at this one. Distribution of weight, 6-month-old baby girls. Yeah, so baby weights, right? When, you know, I don't know if you've had any babies, but when you have a baby, they always tell you their percentile on the height and the weight charts. And every time you go back for the 1-year checkup and the 2-year checkup, they let you know. All right, those are normally distributed, right? There's an average baby girl weight. There's the average amount off of the average, called the standard deviation, and on you go. All right, so distribution of weights for 6-month-old baby girls. Approximately normal with mean boom, standard deviation boom. Use the rule, blah, blah, blah. Same thing. Here we go again. So we're going to draw the normal curve. Going to put the middle. 1 jump to the right, 2 jumps to the right, 3 jumps to the right, 1 left, 2 left, 3 left. What's the middle? 15.75 pounds. Is that the average baby girl weight? 15.75. And the standard deviation is 3. So go up by 3 every time. Up by 3. 18.75, 21.75, and 24.75. And the other way goes, so that was up by 3. I added 3, added 3, added 3. The other way I will subtract 3. 12.75, subtract 3, 9.75, subtract 3, 6.75. Okay, and then the percentages, you know, are always the same. 34%, 34%, 13.5. 13.5, 2.35, 2.35, bless you, 0.15, 0.15. So, okay, so here we go. Suppose that a 6-month-old baby girl weighs 9.75 pounds. Approximately what weight percentile? Oh yeah, this is important. So I hope you're writing this down. This one will have an extra wrinkle that I haven't showed you yet. It's small, it's not a big deal. But they're going to ask us percentile. We haven't really thought carefully about that yet. It's real easy. It's real common in real life. So it's good to, you know, any educated person should know what percentile really means, because they use it in all kinds of places in real life. Percentile, let me say it first, I'll write it down, means percentage below. It simply means percentage below. So let me write that somewhere for you. Didn't spell it right. Percentile is percent below. Percent to the left, in other words. So that's what, so percentile, so you got to get kind of used to that word. Percentile is not just percentage. That's the mistake a lot of people think. They'll think, you know, percentile is just a funny word for percentage. Well, it means percent below. That's what it means, percentile. They use it all the time, especially baby weights. They'll tell you your child's percentile. They don't mean percentage. Or if you take a standardized test, a lot of standardized, the IQ test or the GRE or the SAT, sometimes they'll tell you your percentile score. They'll say, this school district is at the such and such percentile mark. You take the law exam or the medical exam or the big professional exam. They'll tell you your percentile score. They don't mean percentage that you got right. That's not what they mean. They mean percentage of people that did worse than you. Percentage that are below you. So let me quiz you and see if this is making any sense. What if I said I went and took a big law exam and I got 60 percentile on it? 60 percentile. So did I do good or not good? What does that mean? 60 percentile. That's actually pretty good. Because what? Nobody thinks 60%, that's like a D. That's bad. No, it has nothing to do with exactly how many questions. Who knows? We know nothing about how many questions the person got right. But what we know is 60% of the other people that took the law exam that day did worse. It's like you want to get into the big law schools, you got to hit at the 95, 98 percentile, meaning you're better than 95% of the other people that take the law exam. That's all it is. It's a comparison. Same thing with the baby weights. When you say the baby girl's weight was 60 percentile, it means she's heavier than, or the 60% of baby girls are less, below. So she's heavier than 60%. Does that make sense? So it means percent. So 60 percentile means 60% below. So that's pretty good. More than half of you're above average, right? More than half are below you. Does that make sense? So percentile means percentage below. You really should know that. They use it all the time in real life. So percent below. So when they're asking me on this question, the baby girl that weighs 9.75, where's that? Right here. Here's the 9.75 numbers, that line right there. What's her percentile? They're saying, what's her percent left? What's her percent to the left, below? So you just add up 2.35 and 0.15. 2.35 and 0.15 is 2.5% below. She's at the 2.5 percentile. Is that making good sense? So in other words, she's pretty light, right? Only 2.5% of all baby girls have lower birth weight than her. She's pretty light. Pretty light. Is that good? That's what happened. We had tiny kids for some reason. My wife and I are average, but we had tiny kids. And my oldest daughter, she was like at the 1 percentile. Even though she's healthy, she's at she's like really light. And so it was our second child. So about 3 months in, the doctor, it was a new doctor, kind of a young doctor, was checking her, and she had a little bit of blood in her stool. I think the doctor just nicked her on accident. It was nothing, but the doctor didn't. But because of the percent, this is how doctors know if you're healthy or not. Like if you're really extreme, especially light, like Emma was, really light, the doctor is like on high alert. Like maybe there's something. Maybe this isn't, because this is 1 percentile means only 1% of babies are this light. Maybe there's a problem here. Maybe it's not, because this isn't very natural. I mean, it could be, but could be not. So the doctors look. Well, sure enough, so Emma just had a tiny little bit of blood. I think the doctor just nicked her, examined her anyway. This young doctor was just being cautious. I mean, I appreciate her. She was just being cautious. So she's like, I think you better take your girl she set up an appointment for us at San Francisco, with all those really sad, sick children. So, we're like, okay, we thought maybe the doctor was like, I think there's something wrong, because she was so light, and then she saw that little blood. So we took her like 2 days later to San Francisco, all those poor sad children having all those hard things, They put Emma on every machine, checked her, and afterwards they said, no, she's fine. She's just light. So anyway, she's always been. She still weighs, I don't know what she weighs. She doesn't make 100 pounds. Anyway, so it's just the percentage, but percentile means it's very rare, right? That's a pretty low weight. Only 2.5% are less than that. Okay, let's do B here. Question B. 21.75 pound baby girl. What's her percentile? 21.75. So there's 21.75. 21.75 right there. So, and they're asking percentile. So what do I do that? What does percentile mean? Percent below. So if you're looking right here, it'd be this percent, and the rest of the way is 50, huh? Right? Once you get to the middle, the rest is 50, right? So this would be 50 plus, what, 34 plus 13.5. And that's the 97.5. Is that making sense? That easy? Percentile, percent below. Okay, finally, a baby girl is in the, oh yeah, this will be a little more tricky, 75th percentile. And they're giving me the weight. What is it, 17.8? Let me erase some of that stuff around it. 17.8. So 17.8. They're telling me 75th percentile. So 75th percentile, 17.8. Oh no, actually I came up with that answer, didn't I? Anyway, 75th percentile. How do you do that? You know, there's something you should think of right away. Whenever they say 25% or 75%, what should you think? 25% of the way through the ball game. What's that called? Q1. 75% of the way through the ball game. Q3. End of the third quarter, huh? Yeah, so right away, just always be on the alert for that. In this chapter, whenever they throw out anything with a 25% or 75%, you think, oh, they want me to do the Q1, Q3 thing. Yeah, that's always what they want. So when they say the baby girl is in the 75th percentile, now they didn't say percentage, but percentile means percent below, doesn't it? So if you're at the 75 percentile, what does that mean? 75 percentile? 75% are below you. So where are you? Q1 or Q3? You're Q3. You're at the end of the third quarter, right? You could say that next time you're watching a basketball game or football game. At the third quarter mark, you say, we're at the 75 percentile. Your friends will think you're weird, right? But that's true. That's what that means, right? 75 percentile. You're 75. So what? So that's Q3. They're basically asking for Q3. That's what they're asking for. So what's the, now remember that formula I gave you a few minutes ago? What is that? It was mu minus 0.675, right, or plus? 0.675 sigma, that Q3 formula. Okay, so now do we know mu? Yeah, we do, huh? Mu's right here, and sigma's right there. Yeah, just plug those in. So Q3 will equal mu 15.75 plus 0.675. Sigma is 3. Work that out, and round it, you get 17.8. That's how they did that. So they really didn't use the curve at all. Like Jenna was pointing out on that other one. The Q1, Q3, you don't even have to look at the curve, huh? You just use the Q1, Q3 formula. And I recognize that because of the 75%. So 75 or 25, they want Q1 or Q3. Is that good? On that. What does that mean in real life? That means if the baby girl weighs 17.8 pounds, she's at the 75 percentile mark, meaning 75% have weight below that at birth. Okay. All right. So, oh yeah, this whole thing. I forgot about this. Okay. Honest coin, 600 times, variable, no tail, da-da-da. All right, yeah. Okay, I just need to give you the formulas for this. What is it? There it is. Okay, yeah, basically if you anything you do random, it'll do this. You know, if you were to, just think real life with me for a minute. If I was to toss a coin a bunch of times, 10 times, how many heads do you think I'd get? Well, maybe 5, huh? I mean, but, because, you know, half the time it's supposed to be heads. But it wouldn't probably, it might be 4, it might be 6, it might be 3. Right? What if I was to toss the coin 100 times? How many heads would you think? Well, maybe 50, because half the time. But probably not exactly 50. Maybe 49, 48. You know, so my point in all that talk is that if I tossed a coin 100 times, do you think I would get 100 heads in a row? If I did that, say, hey, I was tossing a coin in my office for class, and I got 100 heads in a row. I hope you wouldn't believe me. Because that's like saying I was struck by lightning 3 times on the way to class. I mean, could it happen? Sure, but, it's just not very, it's super unlikely, right? So my point in that is it's the bell curve thing, right? You're likely going to get about 50 heads, maybe 49, 48, maybe 48, but you're not going to get 0 or 100, right? It goes down like crazy, right? It's bell curved. Everything random is. So this too is bell curved. So how do we use the bell curve thing for this? Well, it's like this. If P equals the probability of whatever it is you're talking about, then the mean is N times P. N equals number of times. So N is number times P is probability. So mu is NP, and sigma is the square root of N times P times 1 minus P. So you want to put those two formulas on your 3x5 card, these two right here. So that's how I'm doing the mu over here. I'm doing N times P. And what is N? 6,400. And what is P? It's just a coin. It's an honest coin. So it never lies. No, what that means is it's not weighted. Sometimes they can make dice or coins weighted. Have you heard about that? That's how they cheat, right? They can put a little weight inside of a die, and so it'll tend to be heavier on that side and land and make the opposite number come up, right? Those are dishonest dice. So, so they're saying this is just an honest coin. It's just 50-50. It's just a totally fair, regular coin. It's 50-50. So it's 6,400 times 0.5, which comes out to be 3,200. And the next part, the sigma, is the square root of NP1 minus P. So that's going to be the square root of 6,400 times 0.5 times 1 minus 0.5. Like that. So you guys have your calculators? Could you get that number okay? That's going to be the square root of 6,400 times 0.5 times 0.5. Well, yeah, I'm running out of room here. Let me move this up. Like that. And so this is the square root of 6,400 times 0.5 times 0.5. And so that must come out to be 40. Can you all get that okay? On your calculator? Square root of 6,400 times 0.5 times 0.5?
What do we get, 0.5?
Yeah, it's from the honest coin. The chance of heads is 50-50. Yeah, good question on that one. Yeah, I'm getting the 0.5 from the honest coin, meaning 50% chance of heads, 0.5 chance. Yeah, so P is the probability. If I was rolling a die and I wanted to get a number 2 or something, chance would be 1 out of 6, wouldn't it? That'd be the probability. So it's whatever you're trying to do, P is the chance of that, the probability. Flipping a coin, getting heads, or tails, either one, whatever. They're saying tails, I guess. 0.5. Is that coming out okay on your calculators? Getting the square root of 6,400 times 0.5, and then 1 minus 0.5 is just another 0.5, isn't it? 1, take away a half, is just a half, right? Okay, now ready for question B? We okay? With all that? Well, actually, I'm going to go to a fresh screen. Let me, I need a lot of room. But are you okay with all that before I change screens? It's all well? Okay. So now on the change of, so you just gotta put those two formulas on your 3x5 card. Now, once you have those, now they're going to start asking about chances. So that means I got to draw the normal curve again. So I'm going to draw the normal curve like that. The middle, right here in the middle, and then 1 jump to the right, 2 jumps to the right, 3 jumps to the right, 1 left, 2 left, 3 left. The middle, now what goes in the middle? Well, the mu. The middle's always the mu, and they tell me that's 3,200. And then standard deviation is 40, so the jump from line to line is 40. So add 40, 3,240, add 40, 3,280, add 40, what's that, 3,320, like that, and then subtract 40, what about 3,160, subtract 40, 3,120, subtract 40, what's that, 3,080? Yeah. 3,080. Like that. And the percentages, as you know, are always the same. So 34%, 34%, 13.5, 13.5, 2.35, 0.15, 2.35, and 0.15. Okay. So we good with all that data? See what I did? So what does that mean? That means if you're going to flip a coin 6,400 times, or have a computer simulate it, much more likely, how many tails are you going to get? Well, 34% of the time, you're going to get between 3,200 and 3,240 tails. Right? You're expecting half. Half of 6,400 is 3,200, right? That's the middle. That's why the middle is 3,200. That's what you're expecting. 3,200 tails. But 34% of the time, you're going to get, and on you go. So those are that's what will happen. You know who knows about that very well? You know who has a science of that? The casino industry. They know exactly how the random things are going to happen with dice and coins, and they know exactly, because that's why I always kind of chuckle to myself a little bit. Maybe I'm just cocky now. When people say, oh yeah, look at my relatives, like, oh, we win all the time. Thinking, no, I know math. It's a science for them. They're not guessing on what's going to happen with the game. They know exactly. Some are going to win, some are going to lose. They have all these curves. They tweak them, just the number of winnings they want to allow. They know exactly what's going on. It's a science. So let's answer the question. What's the chance y, which is the number of, y is just the number of tails up here, see? Y is the number of tails. Is going to go between 3,160 and 3,240. 3,160 and 3,240. So from here to here. 34 and 34. So the chance you're going to get between 3,160 tails and 3,240 tails, if you flip the coin 6,400 times, is a 68% chance, right? 34 plus 34. Good. Next question. What's the chance it's going to be between 3,160 and 3,200? 3,160 and 3,200. 34 straight, huh? Final question. 3,120 and 3,160. 3,120, 3,160. It's just 13.5 straight. It's all easy once we have the curve, huh? So even random things are not so random. You ever heard about patterns within chaos or patterns within randomness? There it is. I mean, flipping a coin's random. Sort of. But there's patterns, huh? You're not going to get 6,000 heads. I mean, could it happen? Yeah, and I could be struck by lightning 3 times on the way home on a sunny day. And it could, but it is crazy rare, right? So that's what we see. There's patterns in randomness. Very interesting whole area of math and science to study is the patterns in randomness. Anyway, we don't got time for that. We got a test tomorrow. That's what we're doing here. Coin questions or dice or some kind of random thing on the test tomorrow. And just use the formula. So here we go. They say, okay, mu, what's the formula? It's n times p. So let me let you do that one. I think you get more out of it if I give you a second rather than just whipping it out. So go ahead, give that a try. There's the formula. I've written it for you. Mu is n times p for any kind of random thing. Flipping the die, rolling a coin, whatever. No, you don't flip a die. You roll a die, do it. All those are random. So ask yourself, what's the P? What's the end? Do you know the end? What's the end? The end is 2880. They're telling us that, right? Right at the top, 2880. But let me let you think about the P for a minute. What is it we're doing on this one? Or what's the random thing we're doing? Rolling a die. And what is the result we're hoping for on the die? I want to get the number 1, huh? So if I'm going to roll, if I got a die here, and I'm going to roll the die, and I want to get a number 1, what's the probability? What's the P? What's the probability of that? 1 out of 6, huh? So the P, is everybody good with that? So last time we were flipping a coin, chance of tails was a half, or heads would have been a half, same thing. This one we're rolling a die, the chance of getting a 1 is 1/6. Huh? What if they said, what's the chance you're going to get a 1 or a 2? 2 out of 6, right? What if they said what's the chance you're going to get a 5 or a 6? Well, still 2 out of 6, huh? Right? So whatever we're doing, that's the P. So we want to get a 1, that's 1/6. Here's the N, so the N times the P is 2880 times 1/6, which comes out to be 480. And now can you figure the sigma, which is the square root of N times P times 1 minus P? So square root of 2880 times 1/6 times 1 minus 1/6. So crank that in your calculator, you should get sigma of 20, the standard deviation of 20. What that standard deviation means is average distance from the middle, meaning on average you're not going to get more or less than 20 off the average. That's what that's telling you. We good there to that? Now, can we do B and C? How are we going to do B and C? What am I going to need to do to answer questions B and C? Any ideas? I'm going to need to draw the bell curve. Do the whole bell curve thing. How do I know? Well, because they're talking about probabilities and numbers, you know, and whenever they do that, you got to draw the bell curve. So, okay, if I go to a fresh screen, everybody got that information down? We good with all that? Okay, let's go to a fresh screen and got to come up with the bell curve. So here we go yet again with the bell curve. The middle is the mu, which is the 480. And one jump to the right, 1, 2, and 3 lines to the right. Every line is 20. So you add 20, then 1, 2, and 3 to the left. So 500, 520, 540 go left, 460, 440, 420. Is that good? And the percentages are always the same. 34, 34, 13.5. 13.5, 2.35, 2.35, 0.15, 0.15. Okay, we good with all that? Now come their questions. What's the probability that it'll 540 times? More than 540 times. 540 is right here. More is to the right, right? So it's 0.15, but it's 0.15%, isn't it? Let me just, oops, not what I meant to do. 0.15%. So 0.15%. Remember what you do for percent? You get decimal goes back 2 places, so that'll be 0.0015. Because see, why do we have to do that all of a sudden? We didn't have to do that before. They didn't put a percentage on there. See how this doesn't have percent? They've removed the percent. So you have to remove the percent. You know what I mean? It'd probably be better if I go back. Wait, that's the same thing. There we go. See on this one, they put a percent on there? So they wanted a percentage answer, so I just left it. But if they'd taken off the percent, I would have had to say 0.68, right? Because you move the decimal back. If there's no symbol, when you take it off, decimal has to move, as you know. So when they have no percent here, no percent, then we have to move the decimal. Same thing here. Between 480 and 500, that's 34%, which is 0.34. Oh, they want it 4 places. That's kind of dumb, huh? So you got to put in 2 zeros. That's kind of dumb. So there we go. Is that good on that? Questions on that? So what that means is if you're rolling a die, what if somebody says, yeah, I was rolling a die, and I rolled it 2,880 times, and I got 1,000 ones, like almost half the time. No way. Look at this. The chance you're going to get more than 540 is only 0.15, less than 1% of the time. Are you even going to get more than 540? No way you're going to get 1,000 ones. I mean, just no way that's going to happen, right? So there is patterns in randomness. They call that the law of large numbers. They say, yeah, something random can happen if you just do it 1 time, 5 times, 10 times. But if you do it thousands of times, the laws will start to take over, and you'll see the very predictable patterns within randomness. So on this one, they give you a little table to help. All right, here comes the question. Distribution of weights for 6-month-old baby boys, approximately normal, with mean 15.75, standard deviation 2. Suppose 6-month-old baby boy weighs in the 95th percentile of his age group. Estimate his weight. Estimate his weight. Okay, well, I'm just going to grab the formula. So 95th, that formula right there. Just grabbing the 90. So they give a little table to help you. So grab the 95th thing there. So it's going to be mu plus, what is it, 1.65 sigma? Like that. So that's mu, 15.75 plus 1.65 sigma is 2. Just work that out, and you'll get the answer, whatever it is. It's covered up now, you can't see it, but I'm sure you could get it. Is it 3.3? So is it 18? Is it 19.05? Is that what it is? Somebody got that? I could be wrong.
Yeah.
That it? Okay, thanks. Is that good so far? And then question B. Suppose the 6-month 10th percentile. 10th, so then we just grab the formula for the 10th. 10th is right here. So I'll do part B over here. It's going to be mu minus 1.28 sigma. So mu, what is mu? 15.75 minus 1.28. Sigma is 2. Somebody have that one? No, 13.19? Maybe? I think so. All right? Okay, thanks. Is that okay? Just grab the formulas off the table. Plug them in. Probably the easiest question we've had so far. They're gonna make me do this backwards in a minute. That'll be a little more tricky. So everybody good with forwards? Just look at the table, grab the formula. What they're gonna do here in a problem or two is they're gonna basically give you this 1319 and ask you which one it came from. And so you're gonna kind of have to look and figure it out backwards. That's a little more tricky. All right, so this one's a little more tricky. So, all right, Henry's a 6-month-old baby boy. He weighs 23.05 pounds. Estimate the percent corresponding to Henry's weight. So you just got to kind of guess and check and find the right one. So So let's try to do it smart though, so we don't waste too much time. So look at Henry. Here's Henry's weight, 23.05 pounds. Is Henry more or less than average? What's the average? Yeah, there's average. Henry's above average, right? He's a healthy boy. He's above average. So what? What does that mean? Does that mean, am I going to look at these numbers or these numbers? The left, the high percentiles or the low percentiles? Remember what percent? It's going to be the high ones, right? Because percentile means percent below. So Henry's above the 50 percentile because there's more than 50% below him. Remember? Percentile means percentage below. So if Henry's above the middle, then there's more than 50% below him. So it's got to be one of these, first off. I'm not even going to look at the other side, right? Okay, now how do you know which one? Maybe you just sort of guess. And then you work it out and you see if it's right or wrong. So I'm going to guess maybe he's at the 90th. Okay, so I'm going to try mu plus, I'm going to go 90th. So mu plus 1.28 sigma. What's mu? 19.75. 19.75 plus 1.28 sigma is 2. What is that? 2.56, so 21, 22, like 31 or something? Let me get that number. I'm getting more guessy here. I'm not sure. No, no, I could be. I'm probably wrong. What's the number? Oh, okay. You might be right. Anybody got it? Is it 2.31? 22.31? Is that what it is? Probably got it? Okay. So anyway, so is that what it's supposed to be? What's Henry supposed to be? Is the 90th right? Is Henry the 90th? Well, Henry's 23.05. He's not 22.31. He's higher. So he's not 90th. I'm playing warmer, colder here, right? Am I getting warmer or colder? Do I need to go higher or lower from the 90th? Didn't work. I took a guess. I said maybe he's 90th. I used the 90th formula. I plugged in. I got 2231. Henry's like, no, that ain't me. I'm higher. I'm at 23. I'm not at 22. I'm at 23. So Henry's higher. So I got to go higher than 90th. So then I go, okay. Let me try 95th now. Isn't that the next one? 95th. So I go, maybe Henry's the 95th. Mu, what is it? Mu plus 1.65 sigma. Plug in the mu. The mu is 19.75 plus 1.65. What's sigma? 2. And that's it, isn't it? 23.05. Ding, ding, ding. Yes, we got Henry. Henry is 95th percentile. What does that mean if Henry's weight is at the 95th percentile? What does that mean in real life? So somebody said, you came up with the doctor, our baby's at the 95th percentile. What does that mean? 95% of the babies are less weight, right? 95 or less. Healthy baby. Right? 95% below. Right? Percentile means percent below. All right, good. So and part B is the same thing, right? Paul and da-da-da and do the same thing. Now, Paul's below average, 19.3, so you're going to check these numbers, right? But he's not much below. So he's probably like 40th. That's probably what he is, 40th or 30th. He's not way below. He's just a little below. Right? That good on that? I flash off of that. Okay. 1,492,408 college-bound seniors took a standardized exam, like the SAT or something. Distribution scores, one section, possibly normal, mean. They are. The results of these kind of tests are always normal. So there's the middle, there's the standard deviation. Okay. Estimate the 80th percentile. That's easy. Just grab the 80th formula, right? Just grab it right there. So this would be mu plus 0.84 sigma. Mu is 511. That's the average score in the exam. plus 0.84 times sigma. Sigma is 110. That equals, I don't know, 590 something probably. That good? So part A and part B are cake, right? Just grab the formulas. Let's do C though. That'll be a little harder backwards. Am I going too quick? You want to copy that down? It's 110 there. But doesn't that come out 590 or maybe 600? What is it? 600, 603? 0.14? 603.4? Okay. Like that? Did you y'all get, anybody else getting those numbers? No? 603.4? We good? So, that's easy, right? Just use the formula, no big deal. Let's do part C though. That'll be a little harder. You okay if I flash off that? We good? All right, part C. All right, part C. A test score of what does it say? 540. Yeah, 540 is what percentile? They want to know, again, it's a backwards thing. So do the back. So they're giving me the test score now, right? They're giving me the test score. That's not a percentile, whereas these were percentiles, A and B. C says estimate the percentile, find the percentage that goes with a score of 540. All right, so can you do that? Can you do the 540 thing? Let me give you a second rather than me just whipping it out real quick. So it's a guessing. You got to guess and check, right? But you want to guess with a good plan or guess wisely. $540. So I want to ask you, is 540 above average or below average? Above the middle or below the middle? What's the middle? Middle's 511, right? That's the average score in the test. So 540, this is above the middle, huh? So this is somebody in the higher percent, but not a lot. Not a lot above the middle. It might be 60th or 70th, one of those, Probably, be my guess, And just guess and plug in. So I'd say, what is he at 540? He might be 70th, I don't know. So I'll just say 70th, question mark, maybe. And so I'll go mu plus, what is 70th? Mu plus 0.52 sigma. 0.52 sigma. So what's mu? 511 plus 0.52 sigma. Sigma's 110. How's that come out? What's 511 plus that? 52 and then 5.2. 57. 57.2. 57, 68. Is it 568.2? And that's too high, huh? Did I do that right? That's coming out too high. So he's probably 60th, huh? That's too high? Right, because he's, what is he? He's 540. He's only 540. 568 is too high. So I'm guessing he's the 60th. It's too high. Let's try the 60th. That's mu plus, what's the 60th? 0.25 sigma. So mu 511 plus 0.25 sigma. Sigma's 110. And so that's what, 25 and 27.5. 27.5, 38.5. Oh, yeah, let me help with this. Yeah, that's 538.5. So 538.5, that's not exactly right. But that's where you got to read the fine print on the contract right here. Note, scores are in tens. So 538.5 will be rounded to what? 540. That's him. He's 540. That's the one. He's the 60th percentile. There we go. Is that good on that? So we need to look at the proc exam because there's a couple, almost especially on this exam, there's a couple of tricks that I need to show you. Is it okay if I flash off of that? We all got that down? All right, so here's what I'm going to do. We just don't have time to do it in class. I'm just going to give you this. I'm going to spend the next half an hour doing about, 5 or 6 or 7 of the trickiest ones that we really haven't been over at all. They just weren't in the homework. And then I'll let you take the rest to work on your own. And then tomorrow, what we'll do tomorrow for the first hour, I'll go over this and answer any questions you have. And, I encourage you to look over this tonight. We're going to do the hardest ones right now. But look over the other ones. And tomorrow, for the first hour, I'll take whatever questions you have on it. And then the second hour, we'll take our test. And then the course is over. All right, so there's a few I haven't done with you. So let's do this one right here. Regular 6-sided dice twice. I have not showed you what happens when you roll a die twice. It's pretty simple, but we need a chart. Did we do it in the past? I can't remember. I don't think so. No, I'm thinking of a different class. It's funny, the spring classes they're mixing in my mind with this class. This class has been so fast. I keep thinking we're a spring class. That's not the truth. All right, so anyway, I'm going to make a 6x6 array here. Here we go, 6x6. I made 6x6 array. I just split it in half and then 3 lines on each side. And I'm just going to put all the things that can happen when you roll a die twice. You can get a 1 and then a 1. You can get a 1 and then a 2. A 1 and then a 3. A 1 and then a 4. A 1 and a 5. A 1 and a 6. Or you can get a 2 and then a 1. A 2 and then a 2. A 2 and then a 3. A 2 and then a 4. A 2 and then a 5. A 2 and then a 6. Right? You tracking with me? You can get a 3 and then a 1. A 3 and then a 2. A 3 and then a 3. 3 and then a 4. 3 and then a 5. A 3 and then a 6. Or a 4. 1, 2, 3, 4, 5, 6. Or you can get a 5. With a 1, 2, 3, 4, 5, 6, or a 6, finally. With a 1, 2, oops, messing this up. 2, 3, 4, 5, and 6. Good, so those are the 36 different things that can happen when you roll 2 dice. So when you roll 2 dice, there's the 36 things that can happen. This is what the casino knows all about with the game of craps, with the 2 dice. They know exactly all the probabilities for everything. So, okay. So now we can answer the questions they have. Question number 1. If we roll a regular 6-sided die twice, same thing, roll 2 dice or 1 die twice, same thing. Probability that at least one of the rolls will land even. At least one roll even. So I'll give you a hint. The bottom's 36, right? Because that's the total number of things that can happen when you roll a die twice or 2 dice at once, whatever, same thing. Out of the 36 different boxes there, how many fit their condition? At least one of them's even, right? At least one is even. At least one is even. If at least one is even, the only way that can't happen is if both are odd. So, boom, 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 all of these. Boom, 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 all of these. Boom, 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 all of these. What is that? 18, 19, 20, 1, 2, 3, 4, 27, 27 out of 36. I got to reduce that. Does everybody see how I came up with that? 27 of those 36 boxes have at least one of the 2 numbers, maybe both, being even. See how that is? Right, so if either number is even, so the columns that had the first number even, I just circled the whole column, because they've already got an even number, right? So the column starting with 2, 4, and 6, I just circled the whole column. And the other ones that started odd, I circled when they ended even, because they had an even number. So that's 27 out of 36 results have at least one of the two numbers being even. Now reduce this fraction. Divide by 9, top and bottom, be 3/4. So there's our answer. So when you roll 2 dice, 3/4 of the time you're going to get at least one of the two numbers being even. Is that good? Shall we try question 2? Can we even read it? If we roll a regular six-sided die twice, probably the both rolls landing with the same parity, both even or both odd. Yeah. I should redraw that. Is that okay? Can I flash off of this? You guys got, can I go to a new screen? Got that down okay? So let me go to a new screen. So I'm gonna have to do the thing again. So here we go again. So I'm gonna do 6 by 6. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, and 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and 6, 1, 6, 2, 6, 3, 6, 4. Sounds like I'm a drill instructor. All right. Here we go. All right, so how many have both even or both odd? That's what they're asking. Both even or both odd. Is that what they're saying? Both even, both odd. Yeah. So here, both odd, both odd, both odd. Both even, both even, both even. Both odd, both odd, both odd. Both even, both even, both even. Both odd, both odd, both odd. Both even, both even, both even. 18 out of 36. Divide by 9. Top and bottom, 2/4, 1/2. Half of them. Half of them have both even or both odd. Is that okay? On those? Question 3 down there. If a fair coin is tossed twice, now we're talking about a coin, not a die. The probability that both tosses will come, I can't read that. Come up heads. Okay, yeah. So if you're gonna, so when you flip a coin twice, the coin thing, right? Remember, it's like what we did on the quiz this morning, or right after 12 o'clock. So head, 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 tail, tail, head, tail, tail, right? The 4 things that can happen when you flip a coin twice. How many of those will come up that both are heads? Well, 1/4. Good? Good so far for those 3? So we've seen that before. I was just buying some time while you copy down the rest of that. You got it down good? Can I go to a fresh screen? More important to see the big dice chart again. I'm going to have to draw that thing a 3rd time. Are you ready? All right, here we go yet again. I'm going to draw the 6 by 6 array. So split it, 3 on each side. And split it, 3 on the top, 3 on the bottom. All right, so 1, 1, 1, 2, yet again. Okay, So now there comes our question. What is the probability of rolling a total of 7? So if you're going to roll 2 dice and you want them to add, so I really encourage you to draw this. I'm going to do some important stuff on the diagram, right, that you're going to want to have in your notes. So draw out the whole diagram real quick. And then look at it for a second and tell me, where is there a total? What do they add? The two numbers add up to be 7. Try to circle all the boxes that have a total of 7. Do you see them right here? They're down the main diagonal, aren't they? Sum of 7, huh? They add to be 7. We good there so far? Did y'all see that? So what's probably the, so what is it that it's 6 boxes out of 36? Reduce that fraction, divide top and bottom by 6. It's 1/6. A.